Well, good morning, good afternoon, good evening, everybody. Welcome to the September edition of the IREE community meeting. I want to say, like, I think thanks for all the folks that sort of at the last minute, were willing to present a little bit here. We had a last minute scheduling change that, we'll discuss some of the other components later we want to discuss. But we have a couple of interesting topics today. I'll sort of kick us off a little bit just at the high level to give some folks some time as they're cycling in and whatnot, just to discuss a little bit some of the work folks may have noticed ongoing externally, and also sort of perhaps to get some feedback, or afterwards as well, folks can send with respect to like the model usage. So recently we've been looking at supporting, rather small models, and I think folks have already seen like some of the work like Tiny IREE side, and if not, there's a nice article by like the folks at the Fraunhofer Institute about this. But to this extent is sort of a case where, we have for a couple of customers, they have relatively small models, a couple of small ops that currently we are actually ending up with, Ben will hate me if I say runtime overrates because that's not true. But for creating too many like dispatch regions and actually effectively just lowering it in an inefficient way to be able to execute. And so we've had some ongoing work the last while to look at this use case with both like constrain some of the parallelism we have and to enable executing these with just like less overhead, so less dispatches. And like one of the things we've been pushing on is a quote unquote single dispatch formation approach here, and I'm putting it in quotes because that's not truly possible, but we're sort of like pushing a little bit just to for some of these small models which has relatively low complexity, to be able to execute them in a relatively efficient way. And I think we'll discuss about that in another meeting in a little bit more detail and give some results. But it's sort of an interesting and a good exploration as well of all the different mappings down to like the runtime, etc. But so I think given a lot of the folks are here already, I sort of wanted to start off with some interesting work that's been ongoing in the community, and. We have Ernest here. I believe if I'm mapping the correct images to between the two chat platforms from
that's me.
Yes. So he's from. I'll give him a second to introduce himself, but he's been working on the IREE.gd, which is for Godot. Extension a little bit, and I thought it was just perhaps a good opportunity to actually introduce this to a little bit larger audience and talk about all the things that they've been doing, things that have been working, things that haven't been working, etc. With that, please introduce yourself, and the floor is yours.
Okay, I'm Ernest. As introduced, I've been working on Godot engine for animations and 3D import and export, but somehow I saw IREE being actually I saw the announcement being part of OpenXLA, and it was like this IREE was the solution that I could see for being able to run all, like, I guess many of the compute models on Vulkan compute. And that was the interest I had with getting this IREE.gd. GD stands for Godot, and that's why it's like G.gd. And the idea was that we were gonna try and do a hello world. In this case, the hello world would be a image upscaling task. So we made a small video. Currently, the code only works with the Linux build, and I posted a video. I'm not exactly sure how to play this video on Meet, but it's simple image upscaling where you take a small image and you make it 4 times bigger.
So could you reshare it, and I can queue it up to show it.
Okay, I put it in the in-call messages.
Unfortunately, I joined late on my computer. If you could just
okay, I'll post it in a different channel, and then you can look at it. Okay. Okay, there. So so a few of the challenges was that we needed to get the Vulkan pointer to be able to execute, and that was our main draw of using IREE, is that the group was able to run PyTorch and TensorFlow models in part of machine learning, and then we could run this on ordinary computers that just have a graphics card, GPU, and they have Vulkan, and Vulkan is on a lot of places, given the Vulkan portability initiative of emulating Vulkan on the Mac devices. I guess if you have any questions, I can pause for a bit.
I mean, that looks like a nice demo. So, and this is running with Godot, or how's the integration happening with this one?
So the integration is that we have Godot engine. Godot engine calls this this thing called GD extension, which is a library that uses the Godot API, and then the API is statically linking the IREE code. And then it is running the VMFB, I think, which is the TensorFlow machine model for ESRGAN. So there was we're still having trouble with the Windows build. It was causing us trouble. We found we can probably file those bug reports into the IREE repo.
If it was the issue that was posted earlier, I think there's a workaround, and we can change some things depending on where it's coming from. But we should be able to get that working for you.
Yeah.
And so perhaps towards the level of integration, sort of at what is sort of the granularity or the APIs being exposed by the extension?
Give me a moment. Let me read my notes. So our granularity is that we want, previously our design was to expose specific objects like images and what's it called, float arrays, but we did some exploration and that didn't work. What we ended up with was getting a function name and then returning a byte buffer, and then we interpret that byte buffer as, say, float 32 of some size as the input or output. Does that answer your question?
Yeah, so I mean, from the compilation is in a way so offline VMFB is effectively that's sort of what's being distributed, and then it's rather low level F32, so it's sort of the current interface supported. That's sort of right. Yeah.
So the VMFB is the thing that is being distributed. We're currently targeting Vulkan compute, but in theory, we can probably run on the CPU too, degrade even more.
Okay.
The second part was that basically interpreting byte arrays arbitrarily because we have no idea what the byte arrays are, and it's not just a byte array, but it's like an array of byte arrays. So it's like arbitrary. We have no idea what's in there until we like get a model description from the model authors.
So in a way that would require sort of like passing in a signature along with this kind of thing. Is that what you're thinking? Yeah. Yeah,
and I believe that's something that you told us earlier that you could, what was it called? Interrogate the model to find those function names and its input outputs, and that's kind of the route we're going.
Yeah, so I mean, I think also there's a couple of things that there's a PR of mine pending that I've been meaning to write a doc for with respect to like reflections as well. But yeah, I think it is a good question to Stella's point. In a lot of these cases, guessing F32 is probably a good guess. But I mean, I think this is a good point. With respect to being able to actually query what. I mean, this won't work in the full generality, but in quite a few of these cases, we have enough information that we can propagate that you can just utilize the signature of the query. But yeah, I think there's one or two gaps there still that we need to address to just make the common case simpler.
Yeah, I think I still have having worked in the TF Lite ecosystem for a while. There's especially when starting to get into integrations like this in applications, unless you build a whole framework to handle every possible combination of data types and channel layouts and planar and interleaved and stuff, like there's never going to be a case where you're going to handle anything that reflection can give you. And so I think the question then really becomes why try that route? So I'd be interested to know, what the expectations are here around usage of this stuff. In a game engine kind of scenario, you wouldn't expect to be able to load an image, and that image could be one of 10,000 formats. You would say, I support one of these 4, and then you would pick a model or adjust the model to support those formats you have.
Well, you would say you pick a model, you figure out its signatures somehow by interrogating the model or asking the author or some way, and then you probably will, like, let's say it's the image, right? Because this is the image upscaling demo. It could be HDR, right? And then you would have to get something to form that 0 to 256 value that the float, or maybe it's not actually 0 to 256 floating point. It's actually 0 to 1. But that was something we had trouble with during our testing.
Yeah, and I think that's where there's the interrogation of a model at rest on disk of like your original model and doing like a TF Lite dump of the flat buffer or their metadata JSON versus something runtime dynamic of you in your application binary, your Godot binary, are trying to figure this out on the fly. I think
I treat this more like you are quote unquote buying a model from a store, and it will have like it will tell you that it has this food, has this whatever, and you kind of expect the distributor to get that correct. And then once it's correct, as long as you upload the inputs, it probably may get the right outputs.
Yeah, it's similar. You go to the Unity asset store and you download some asset pack, and knowing that something is in an FBX format versus an STL or an OBJ or whatever. I think like being able to classify, like traditionally in ML, people will defer that all the way to the runtime and then have to compile in an OBJ loader and an STL loader and an FBX loader and so on. I think if you're able to treat it like that as kind of like the content acquisition versus and then you get that into the right format, and then you go to use that at runtime, that gives you a flow.
As a side note, we actually had to write an OBG importer, FBX importer, so on and so forth.
Yeah, because one of the things that you can do, given that we're a compiler here, is instead of needing to adjust your application to fit what the model has, you can adjust the model to fit what your application needs. And so that might mean something like, whereas you're interrogating the model to figure out its HDR and that you need to apply scaling, and so you would still call into the model the same way you'd get the result out, and then you would have to go to apply scaling. This would be something like writing a function that applies the scaling and compiling that together with the model. And so from an application perspective, you're just calling in, you're getting whatever you wanted. You said, I want RGB, sRGB, back. But it gives you the opportunity to not then have to write all that code to do the format conversion and stuff on the application side, but also the potential for that to be fused into the model itself. Yeah. So when the model is actually producing the outputs, it produces them in what you need.
That becomes like from the point of view of Godot, that's a black box part of the model, and you just adjust what the input is at that point. Let me try that again. It means that instead of pre-processing on Godot's code, we assume it's a black box on the model end, and we just adjust what the input is given to the model. Like, it's still like a preset format. It's just a different preset format.
Yeah, I think anything works. It's really like in these kind of pipelines at scale. Like if you were doing this to every texture in a scene, you would not want and the textures were in format because they were like a compressed texture format or something like that. You wouldn't want to be decoding them, decompressing them, swizzling all the bytes, de-interleaving them, so on and so forth to run the model every single time. You really want to kind of optimize for reducing the number of copies you're doing and then the amount of duplication you're doing. And so treating the model as a black box kind of prevents you from doing that. You're always going to need to adjust to get into whatever the model wants, when what we have here is the ability for you to make the model isn't a black box anymore. That you can make the model do whatever you want. And if you treat instead the Godot side as the black box of whatever textures Godot is giving us in whatever format Godot is loading them in is what they need to be. And then you change the model to adapt to that. You've now removed the need to copy, the need to marshal the data, the need to kind of duplicate things.
There are trade-offs. Like Godot has at least two versions of the data. There's the pristine, like from source art version, and there's the heavily compressed for runtime version. So I would assume that the heavily compressed for runtime data set will make the black box IREE model perform worse by definition. Like it should perform worse.
It should perform better, and only if you don't treat the model as a black box, basically. Right.
I mean the slider. There's pre-processing in Godot that you could do that will turn your data into garbage, but it will be just good enough for the target platform. And you could also do the same thing on the machine learning side, where you take a very dense input and output a very sparse output. Like it's a tuning thing. Like you want to go all the way. You want to choose what trade-off you want. And I agree with your point that making the IREE model not a black box would help tune that part if needed.
Yeah, it really depends, on the use case, and is this a experimental kind of platform for tuning, or is this something actually integrated into a game? And if it means your load time can be 10 times less because you're directly using the data in memory and you don't need any additional memory and stuff like that, that's a trade-off versus being able to sit and drag a slider around and have that go because you're doing it all on the fly. So yeah, I think you're right. It's just a trade-off.
And there's many times you can make the trade-off. You can make it at the programmer level. You can make it at the artist level. You can make it at the runtime game loading level. You can also do all these same things on the model side too. you can train, you can reduce the quantize. There's like options too. Yeah, I agree.
Yeah, and I think the fun thing that you'll be able to play with here is we ran into this on the TF Lite side of, you know, when the models were treated as black boxes, someone would have an image in some Java bitmap, and you know they would then read that into a Java array of integers, and then they would create a Java array of floats to then go in Java in a loop to divide those out to you know, and then they would pass that into the model, and that of course was then then terrible. It was, you know, we had benchmarks where it was spent longer manipulating the Java arrays to get the data in the right format than to actually run the model. And you know what you can do with something like IREE is you can still treat the core of the model as a black box, but you can add that shim function. What they were doing in Java, you know, serially locking each element in a Java array. If you were to write that in IREE, which means in HLO or TF Lite or whatever, we would then compile and run that in parallel, you know, and do that very efficiently.
So I'm going to interpret this in a different way. So in JavaScript, by moving that array code, you're basically turning IREE into a very fast multi-core, multi-process SIMD library.
Yep,
basically.
Exactly. And if you're compiling that to Vulkan, then we'll run that on the GPU, and so the data will never leave the GPU through the whole pipeline. And so I think like that'll be the fun stuff that you start to get into, of if you find yourself, you know, having to write a bunch of code to do that kind of data manipulation, you can effectively think of those as little tiny models, and the model might just be like a divide and a conversion, data conversion or something. But then if you compiled that, we'd generate the Sphere V shaders. We would schedule them with Vulkan. We could do it asynchronously along with the model invocation itself.
So we thought of that. We thought of basically treating this in this specific like use. We would be treating IREE as a linear algebra library that's been accelerated.
Exactly.
And that's something that Godot is missing, because writing compute shaders is hard. Well, but some people like writing Python for the compute shaders for ML.
Yeah.
So yeah.
Yeah. Oh, I mean, I'll cut the discussion a little bit short because I want to give Harsh some time as well. But you know, I think this is actually a very interesting discussion, and I think would make for, you know, both a good showcase of some of the things we can do here, as well as help push the limits of the support, you know, our side. So, you know, I'm quite excited to see that, you know, the initial work here and things take the form. Yeah, I think we'll probably have we'll try and have a follow up in a couple of community meetings, just to, of course there's the Discord, etc., of course, but you know, just because I think this is quite interesting for a lot of folks here. Yeah, and I just want to say, I saw Harsh join as well. You know, like, so I want to thank Harsh. He actually had to change flights to be able to make this meeting in time, so much appreciated. And Harsh will talk about a little of the ROCm work.
Thanks, Jack. Yeah, really interesting stuff, and excited to see where the integration goes with the game engines. Mine a little bit different, but you know, hopefully also somewhat applicable. But just kind of going to go over some of the work I've been doing on the ROCm side of things. Let me present my screen, and you know, we can keep this interactive. So you know, feel free to interrupt me if you have any questions or comments. All right. Let's get started. I don't think you guys can see my screen. Can you?
Not yet, no.
Okay. Let me try again. 1 second. Sorry. Just give me a few minutes. I think every time I try and present the screen, it just logs me out of Hangouts. So let me try on Chrome or something like that. Or yeah, give me just a minute. Thanks.
Remote presenting is still not a solved problem. I mean, if it's a doc you can share with me, I can also try presenting from my side.
Yes. Yeah. Can I? Yeah. Let me try sending it to you. Thanks. Give me 1 second. I'll just file. Okay. I just sent it to you. Did you get it, Jack?
I'll check in 1 second.
On Discord.
On Discord. Okay.
Yeah.
And just do that. Our downside of having so many folders, man. Okay.
Cool. It should be a PDF.
Yes.
Yeah. Okay. Perfect. Awesome. Thank you. I can see that. Great. So thanks, Jacques, and thanks everyone. So today I'll just be talking about, high performance matrix multiplication on AMD RDNA 3 GPUs. So, as you all are aware, matrix multiplication really is the core computational unit of neural networks. Something like 80 to 90% is often what's quoted. And so as a result of this, every GPU or custom accelerator has something special for matrix multiplication, right? NVIDIA has Tensor cores, and AMD has something similar, right? And so they have these special instructions. So before we get to that, I just wanted to introduce a little bit about the AMD GPUs for the uninitiated. So they're usually categorized in, there are two different categories. One is the gaming optimized or RDNA GPUs, and the other is the compute optimized. These are the data center class GPUs, and this is CDNA. So our goal is to target both, but in that journey, we're going to start with RDNA first. RDNA has WMMA instructions. That's what they use for matrix multiplication. And CDNA has something called the MFMA instructions. Very similar, but different. So the goal right now is to bring up the ROCm backend in IREE. And to start, we want to start with a matrix multiplication example and really try and see what kind of performance we can get. So the card that we're looking at is a AMD Radeon 7900W with about 123 teraflops of half precision compute. And so the goal is to see how close to that we can get. Next slide, please. So let me talk a little bit about the entire pipeline. This is just a graphical description of how it works. So the very first thing we do is, we take this math model, which is either expressed in the linear dialect or something similar, linear on tensors, and then we tile it to work groups using SCF for all, tile the reduction dimensions, promote the operands A and B in this case to shared memory, tile to warps, again using SCF for all, vectorize, bufferize. Then we do the vector distribution using layout analysis, and then we do pipelining. And of course, in here, the things that I haven't mentioned are optimizations, reducing shared memory bank conflicts, swizzling, things like that, split gay, but those can definitely be added. But this is kind of the skeleton of the pipeline that we're using currently. And one thing I'd like to point out is, a lot of these, in fact, all of these boxes except the yellow box are somewhat hardware agnostic, right? The distribution is really where we go from the vector dialect to something that is more specific. So if we were targeting NVIDIA GPUs, we would go to the NVGPU dialect. And if we were targeting AMD GPUs, we would go to the AMD GPU dialect. So what I will do in the subsequent slides is I will show you the IR before the yellow box, and then we'll spend some time kind of talking about how we kind of went from the vector operators to the corresponding AMD GPU operators. And we'll do so by using the high dimensional layout stuff that I talked about a little bit earlier, but I'll kind of review that again in the context of the current work. But before we get to that, I'd like to talk a little bit more about this pipeline that I just graphically depicted and showed you. Well, how is that actually implemented? And it's currently being implemented using the transform dialect. And the transform dialect essentially exposes a bunch of building blocks that you can use to build your own code gen pipeline. And that's exactly what we're doing in this particular case. So on the right, you can get there's an example of a code gen spec file. This is what I'm using, but it's missing a lot of the operators. But just to get a sense for how it works is you specify a sequence of these different ops. You have the first thing you do is you try and match the kind of op that you're looking for. In this case, I'm looking for a matmul transpose B. Then you can tile and distribute to work groups. And in order to do that, I'm using the transform structure tile to for all op, and so on and so forth. So there's a whole bunch of primitives that already exist in the transform dialect upstream or in IREE that can enable you to build whatever code gen pipeline that you'd like. And on top of that, one of the advantages of the transform dialect is you can add your own operators. And so we do that here as well. But just to close it out, in addition to tiling, there's a couple of other operators in the transform dialect that are pretty useful. One of them is vectorize and the other one's bufferize. So if you go back to the picture that I showed in the last slide, essentially each one of these boxes really just corresponds to a transform dialect op. So if you wanted to create your own pipeline, you could do that and branch off and break off and make whatever you'd like. Thanks. So as I mentioned, this is the IR right before vector distribution, and it will probably look familiar to most of you. We have an SCF4 at the very top. This is kind of the tiling of the reduction dimension. And within that, you can see that there's the memory promotion. That's where we promote the A matrix and the B matrix to shared memory, and followed by transfer reads, the actual contract, which represents the MMA operation. And this happens inside the for loop. And once we're finally done, we have the vector transfer write. So this is going to be the starting point of our journey from the vector dialect to, I guess, the GPU specific dialects. And we're going to do that by using the layout information that is really specific to each hardware. So let's go a little bit more into the layouts and kind of review that. So what I presented last time was, well, not in this meeting, but in another meeting, was kind of the idea that the layouts, the layouts of data in registers for these MMA instructions can be represented using a high dimensional layout. So on the right, what you see is a very colorful image, but what it also represents is the layout of data in registers for the MMA sync operation for NVIDIA GPUs. And I've kind of labeled it, using vectors and lanes, but essentially you can think of these layout representations as representing a mapping from the row and column space of a matrix to a high dimensional space, which is characterized by vector dimensions, lane dimensions, and batch dimensions. So in this particular case, you can see if you walk along the columns, then the elements of the vector can get grouped together into a vector X dimension. Then different threads own these different vectors, and so you have a lane X dimension, and then you have a vector Y dimension. You do the same thing for the rows as well. And so this is kind of represented in the layout that's captured in the table at the very bottom with the red and yellow, where red represents the row dimensions and yellow represents the column dimensions. So kind of, I want to motivate what's kind of the reason for doing something like this. And the reason is once you have captured the layout, then the idea is that vector distribution and the lowering from vector to any of the GPU dialects should in theory be a mechanical process, because all the information you need should be captured in the layout. So for example, if you were doing a reduction along, let's say in this case, columns, the yellow thing, then you would know that there are 8 lanes involved in the reduction, and then you would emit the appropriate code. Right? So that's kind of one potential motivation for this. So if you go to the next slide, you can see that this same layout representation works for the B and C matrices, and this is what I've shown previously. In the previous work, we showed flash attention, and that was specific to NVIDIA's MMA sync operation. But one of the big questions that remained after that particular exercise was, does this layout representation work for other GPUs? And so, that was something that I was very interested in. And this AMD opportunity gave me an opportunity to answer that question. So if you go to the next slide, you actually see the layout of the data, the A matrix for the WMMA instruction for RDNA 3 GPUs. Now this is in a little bit different layout from the other pictures that I've shown, but let me explain these images a little bit. On the left, you have just a regular row major view of the matrix, right? It's an M by K matrix. So that's, when you think about linear algebra and matrix multiplication, this is typically what you expect. On the bottom right, you see how this data is represented in the different registers. This is the VGPR view for wave 32. So AMD GPUs have the ability to change the subgroup size from 32 to 64. So in this particular case, it's 32. So some things to note here are the data is stored. It's a 16 by 16 matrix, but there are 32 threads. And so the data needs to be replicated. And that's shown in the image there as well. So lanes 16 to 31 essentially just replicate the data from 0 to 15. But if you look at this layout, you realize that it's actually much simpler than the NVIDIA layout, right? You see that the first row is kind of held or owned by lane 0, the second row by lane 1, and so on and so forth. And so we end up with a very simple layout that's shown in the box in the table below in yellow and red. If you go to the B matrix, you see that it's very similar. Once again, you have on the top left, you have the linear algebra view. On the bottom right, you have the register view of the data. And once again, there is replication involved. But in this particular case, you can see that the B matrix is transposed in the sense that lane 0 actually contains the columns and not the rows. So this kind of leads to the natural interpretation that the data should, or the matrix multiplication should be in the A times B transpose format for this to work. If you go to the next slide, you can see the C matrix, and this is a little bit different. So you can see that on the top left, again, C is a 16 by 16. But when you look at the register view, it's more like an 8 by 32, where each V0, for example, has 2 rows of the matrix, right? So this changes the layout a little bit more complex, but once again, not really as complex as the A matrix or as the MMA sync layouts that we looked at previously. If you go to the next slide, some more additional details about WMMA. So it comes in various different types, F16, BF16, INTs, so on and so forth. But for now, we're just focusing on F16, A, B, C, and D matrices. And luckily, there is an operator for this already in the AMD GPU dialect. It's the WMMA op. But something to keep in mind in this particular variant of the WMMA op, even though you feed the each thread has 16 elements of the A matrix, each thread has 16 elements of the B matrix, the result that it gets, even though it contains 16 elements, only 8 elements of those are valid. The rest is zeros. And so the determination of which elements are valid is controlled by an attribute known as the subword offset. If it's 0, then the 0th, the 2nd, the 4th, etc. are the valid values. And if it's 1, then it's the 1st, the 3rd, and the 5th. And so when you get the result from the WMMA op, you have to extract the correct elements to get the correct result. Great. And something else to mention is, as I mentioned, the transpose B form is really the more natural form for this. And the other advantage of that is it allows you to load the A and B matrices 8 elements at a time. And so you can really leverage those load, 128 instructions for maximum performance. But that being said, you can also try different variants. If you consider this as a matmul transpose A, now, sure, you don't have the high width loads, but you're still loading just one element at a time, and there could be potential benefits for this. And right now, at least the way the pipeline is implemented, it's not opinionated, and so it's easy for you to switch out transpose A and B by just setting a parameter, and what it does for the layouts is it changes the layouts of the row and the column. So keeps the flexibility open right now while we're still in the phase where we're trying to get maximum performance. So now that we know a little bit about the WMMA op, we know a little bit about the layouts that we use, the question is, well, how can we use the layout to distribute the reads and writes? In the past, for the MMA sync operation, we did memref.load, we extended to LD matrix 1, 4, and so the question is, what do we do for AMD GPUs? And we want to consider two particular cases. The first one is when you load from global memory to registers, and in that particular case, if you just use the memref or the vector variants of load and store, you end up with these flat instructions. The flat instructions, based on the RDNA 3 ISA reference manuals, say that they issue instructions simultaneously in global and shared memory at the same time, and this is not desirable. So there could be potential reasons for why this is happening, but this is definitely something that needs to be resolved. As a temporary interim solution, we can use the raw buffer load or store instructions in the AMD GPU dialect. And so that's one of the things that we do. In terms of load and store to shared memory, what they call local data store, LDS, the memref load store and vector versions of the operators do produce the appropriate DS load stores. And we can adjust the number of elements. So that part seems to be working okay. If you go next to contractions, in the case of the NVIDIA, we mapped it to MMA sync, and here we're mapping it to the AMD GPU WMMA op. Only things that we need to take care of are, first is we need to extract the appropriate elements, as I mentioned, depending on the subword offset. And the second thing that we need to do is make sure that we account for the batch dimensions and accumulate the result along the reduction dimensions, just like we did in the other scenario. And so the last bit of information that we kind of need to keep track of is the barrier ops. So the barrier ops are key to make sure that we don't have any read after write or write after read conflicts. And in order to do that, we make heavy use of the GPU barrier op. Unfortunately, when you lower this op down through the LVM GPU, AMD GPU backend, you end up generating these buffer GL0 invops that basically invalidate the shader L0 cache, and not really desirable. And so instead of using the GPU buffer op, GPU barrier op, we have to use the AMD GPU LDS barrier op. And that gets rid of those operators and gives us the nice S barrier ops that we're looking for. Another thing to consider, so initially the motivation, if you look at it just from the perspective of MMA sync, there isn't too much of a justification for the layout representation. It could definitely be accomplished several different ways. But when you think about more complex ops like flash attention, that makes you realize that it is really important to keep track of these layouts. In the case of the NVIDIA MMA sync exercise that we did previously, what happened often was, well, since we had two matmulls, the C matrix, or the result, the D matrix of the flash attention, of the first matmull was reused as the A matrix of the second matmull, right? And so what that ended up doing was it ended up creating some sort of layout conflicts, because the layout of the C matrix is not the same as the layout of the A matrix. In the MMA sync case, we were able to resolve those differences within each thread. We didn't have to make any copies to shared memory, or we didn't have to do any shuffles between the different warps. But looking at the differences between in the C matrix and the A matrix layouts in the WMMA scenario, it's likely that we will have to do something like that. That's not to say that it won't work. It might be less performant, but it's just something to keep in mind. And also kind of shows you how the layout stuff can be used to kind of guide some decisions about the hardware layout. So if someone were experimenting with different layouts, we could easily run this analysis through and determine whether or not this would result in an extra chip to shared memory or require extra communication between the warps. Thanks. So to conclude, I think the idea was, we wanted to extend this high dimensional layout to more than just NVIDIA architectures, and we did so with the RDNA architecture. We are currently evaluating the performance of this approach and adding additional performance optimizations. As I mentioned, we have added padding to avoid bank conflicts. We're working on the shared memory swizzle, etc. One of the other things that's still present that we're still working on is kind of moving from this implicit layout representation to a more explicit layout representation. When I showed you the IR, there was still vector ops, but there was no vector.layout op, right? And so the idea is maybe we could have a vector.layout op with regions that contains, and so ops that have the same layout are grouped within the same region. So this is one particular direction we'd like to take it. And then the other thing that we were thinking about was how could we extend this to CDNA GPUs as well, since the MFMA instructions, the layout for the A, B, C, and D matrices is very similar to the RDNA GPUs. Could we take all the learnings and all the work that we've done on RDNA GPUs and have it scale to CDNA GPUs as well? Cool. I think that's it. Thank you. A lot of people have helped. And if you have any questions.
I mean, I think I have a basic one. So you mentioned on like the barrier load lowering. Is this actually something that, upstream is intentional? Did they intend to have this invalidate lowering, or is this just a conservative one that they did? And, we should be filing a bug.
I'm not sure. My guess is, they're probably being conservative, something like that. That's probably the same that's happening with the memref loads and stuff that become flat loads. So that's kind of my guess, but we're in talks with some of the AMD folks, and we're trying to see what's going on there.
Oh, sorry, I'm just playing around. I'm just noticing if I switch tabs, the display gets weird, which is just like, really? Awesome. Thank you very much. This is great. I think it's good to see like these things applying to like the different domains and with the different layouts. We have a couple of minutes left. If folks have more, general questions from the community. Our next meeting is actually already on the calendar. For a change, I did that right. On a community calendar, I should mention. So folks, please subscribe to it. If they want to see it, I'll send out the emails a little bit earlier next time. But yeah, if anybody has, any questions, something they want to discuss more generally, the floor is yours. Well, awesome. Okay, thanks everybody for joining. It was great to see everybody in the meeting and for the nice active discussion. And yeah, with that, I'll stop the recording.